Ever wondered what the center of our planet, a high-performance engine, and maybe even a planet made of diamonds have in common? Well, the answer is actually hidden in a set of secret maps. These are the maps that scientists and engineers use to literally build our entire modern world. Let's dive in. Okay, so let's start this off with a bit of a puzzle. I want you to picture three wildly different things. First, the crushing, unbelievable pressure at the very core of our planet. Second, some distant exoplanet that might be made of pure diamond. And third, a finely tuned, high-performance car engine. Seriously, what could possibly connect these things? The answer, and believe me, this sounds a little strange, is hidden inside a very special kind of map. We're not talking about a road map or a world atlas here. This is a map that charts the very behavior of matter itself. So what is this secret map of materials? Well, scientists have a name for it. A phase diagram, and it's honestly one of the most powerful tools we have for both understanding and creating the physical world all around us.
But before we can read the map, we need to know the lingo. And the key word here is phase. A phase is really just a distinct physical form of a substance. The classic example you learned in school is water, right? You've got solid ice, you've got liquid water, and you've got gaseous steam. They're all H2O, just in 3 different phases.
To really see how these maps work, let's start with a simple one for just a single, pure element, iron. This diagram is going to be our key to understanding all the basic rules. Okay, so these maps all work based on one really simple, elegant rule. You see all the lines separating the different colored regions? Each one of those lines represents a point of perfect balance, what scientists call equilibrium. It's the exact recipe of temperature and pressure where 2 different phases can exist together in perfect harmony. And boom! This right here brilliantly explains the first part of our puzzle. See, here on the surface of the Earth, we know iron as a solid we use for buildings, or as a liquid when it's molten hot. But this map shows us that under the insane pressures and scorching temperatures of the Earth's core, a totally different, super dense solid phase called epsilon iron is the one that's most stable. That's the stuff. Scientists believe it makes up a solid mass weighing something like 10 to the 23rd kilograms right at the center of our world. So that's a pure element. Pretty straightforward. But, most of the materials we actually use are alloys, mixtures, like steel. And when you start mixing elements together, the rules of the map, they get a little more interesting. So how does that rule of balance change? Well, it gets a bit more sophisticated. For a pure substance, it was all about having equal energy. For an alloy, a mixture, balance is achieved when something called the chemical potential of each ingredient is equal everywhere. Chemical potential, what is that? The absolute best way to think about it is like atomic peer pressure. Atoms just have this natural tendency to spread out. They want to move from an area where they're really crowded to an area where there are fewer of them. And that keeps happening until that pressure to move is the same everywhere. It's just the universe's powerful drive towards balance. So what this means is that for an alloy like steel to be stable, every single ingredient has to find its own happy place. The chemical potential for all the iron atoms has to be the same everywhere. And the chemical potential for all the carbon atoms has to be the same everywhere. Every single element in that mix has to find its own equilibrium across all the different phases. Now, this is where it gets really fun. These maps have special points of interest, landmarks almost. They're like secret recipes hidden in the landscape. And one of the most important and useful ones is called the eutectic point. A eutectic is this kind of magical mixture. It's a very, very specific recipe of elements where, when you cool it down from a liquid, it doesn't get all slushy or freeze gradually. No. Instead, at one single, precise temperature, the entire liquid transforms into 2 different solid phases, all at the exact same time. Just let that sink in for a moment. It doesn't get partly solid or mushy. The whole thing solidifies. All at once. And that one single property turns out to be incredibly useful for manufacturing and engineering. And this is exactly how we solve the rest of our opening puzzle. Think about the solder used in electronics. It's a lead-tin eutectic alloy. Why? Because it melts and solidifies cleanly at a single low temperature, which is perfect for joining tiny, delicate components. And that high-performance car engine? The engine block is often cast from an aluminum-silicon eutectic alloy. It's lightweight, and because it solidifies so cleanly and predictably, it's perfect for casting strong, complex shapes. So far, we've been looking at pretty simple 2D maps, which are great for 1 or 2 elements. But modern materials are way more complex than that. So what happens when we go beyond the 2D map? Well, if you add just a third element to the mix, our nice flat map suddenly pops out into 3 dimensions. You get these really complex triangular prisms that are much, much harder to read and visualize. And what about the superalloys they use in jet engines? Those can have 10, 20, sometimes even more elements mixed in. It's literally impossible to draw a map with that many dimensions. So today, scientists and engineers don't even try. They use powerful software that calculates all that data directly, figuring out the stable phases, their compositions, their proportions, navigating all that complexity with pure computing power. So in the end, these secret maps are so much more than just charts. They are the fundamental recipe books for matter itself. They contain the instructions for creating the materials that build our entire reality. So now that you've had a little peek inside that recipe book, what would you create?